Welcome to Revised Chemistry with Mr. B. In this video I'm going to take you through the whole of the structure and bonding topic. That's if you're studying for Combined Science or Trilogy with AQA. If you're studying with a different exam board or you're studying for separate science, just check your revision guide to make sure there's no other extra little bits you might need to know. For your GCSE, you still need to know about the three states of matter, which is solid, liquids and gases. And you need to know the particle model of these three states of matter. In other words, how are their particles arranged? So in a solid, it's a regular pattern. The particles are in nice neat rows and they're very close together, and all the particles do is vibrate on the spot. They don't actually move from one place to another. In a liquid, the particles can move around. They move around slowly, and you'll notice some spaces between some of the particles. So they're slightly further apart, but notice how most of the particles are still touching the other particles. So they move around slowly in a random arrangement. Gases move around quickly in a random arrangement, and this time there's much more space between the particles. Now on your exam, you sometimes ask what are the limitations of the particle model, in other words, what's wrong with it? And the first limitation is it doesn't take account of any forces between the particles. There are strong bonds between solid particles and weak forces between liquid particles. It also assumes that the particles are all spherical or circular shaped, whereas in actual fact, many molecules aren't that shape at all. So what we're going to look at now is changes of state when, for example, a solid melts into a liquid, or a liquid boils or evaporates and turns into a gas. I'm starting with a beaker of ice with a thermometer in, and I'm going to heat that up with a Bunsen burner, and I'm going to leave that going until it's fully melted, and I'm going to continue heating it when it's a liquid and keep going until the water starts to boil, and I'm going to track the temperature change every minute as I do that. If I was to take those temperature readings and plot them on the graph, we'd get this quite unusually shaped graph. We'd expect, of course, the temperature to steadily keep increasing of the ice and then the water because we're heating it up with a Bunsen burner. But this is the shape we actually get. If the ice started off at, say, -5 degrees, when we start heating it with the Bunsen burner, the temperature does start to increase. But during the process of melting, when the ice is changing from a solid to a liquid, we notice the temperature stays the same. And during that time, the heat from the Bunsen burner is being used to force apart the particles and overcome those strong forces of attraction. Once it's fully melted into a liquid, the temperature then quickly increases until we reach the boiling point of water. And when the water starts to boil, again we've got a change of state and we notice the temperature stays the same. So this shaped curve, where we've got plateaus or level parts where there's a change of state happening, we call that a heating curve. The first type of bonding I'm going to talk about is ionic bonding. And ionic bonding occurs between a metal atom and a non-metal atom. So if we take the case of lithium reacting with fluorine, we can see lithium has one electron in its outer shell, as we'd expect because it's in group 1. So to become stable with a full outer shell, lithium needs to lose that one electron. Fluorine, on the other hand, is in group 7, so it's got 7 electrons in the outer shell. So this time fluorine needs to gain one electron. So lithium gives its outer shell electron to fluorine, so it transfers one electron or gives one away to fluorine. And they then turn into ions. So if we draw what the lithium ion would be like, it now only has that full inner shell. Now it's given away that one electron. Remember to draw brackets around ions, and that will become a 1+ charge. If you're not sure how to work out the charge on ions, check out my previous video. I'll put a link up here now to that. Fluorine has gained this extra electron, so fluorine turns into a fluoride ion. Notice the slight name change to fluoride. Still got the electrons it had before, 7 on the outer shell, but it's also got this extra one here, which I'm showing with a cross, because this electron came from lithium. And the fluoride ion will now be a 1 minus ion because it's got that extra negative electron. We've got a positive ion and a negative ion, and these two will attract each other together. That's called an electrostatic force of attraction, and it's a very strong ionic bond. Here's a slightly different example. We've got magnesium reacting with fluorine this time, and we can see magnesium has got 2 electrons on the outer shell of the atom, so this time it needs to lose 2 electrons, whereas fluorine still only needs to gain 1 electron. So what happens is magnesium gives one of its electrons to the fluorine atom, so that becomes stable. However, magnesium still has another electron to give away. That will have a full shell once it gains this electron. So what has to happen is it needs to react with another fluorine atom. So exactly like the other one. So this one can now accept the other electron that magnesium needs to give away. And then let's have a look at the ions that they would turn into. So we can see the magnesium atom has turned into a 2 plus ion now that it's given away those 2 electrons. Each of the fluorine atoms have turned into a fluoride ion. Each one of those is a 1 minus ion. But we've got 2 fluoride ions because remember, each one of those has accepted an electron from magnesium. So the formula for magnesium fluoride would be MgF2, which shows that for every magnesium we need 2 fluorine atoms. In an exam, you could be asked to explain how they react together by talking about the electrons. So you would just talk through the diagram saying magnesium loses 2 electrons to become an Mg2 plus ion. Each fluorine atom accepts 1 electron or gains 1 electron to become a fluoride F minus ion. And you need to explain that it's going to take 2 fluorine atoms to take those 2 electrons from magnesium because each fluorine atom can only take 1 electron at a time. If we want to work out the formula of an ionic compound, we can use the crossover method. So for example, aluminium oxide. First of all, we write the ions underneath. So aluminium would form a 3 plus ion because it's in group 3 of the periodic table. Oxygen would form a 2 minus ion because it's in group 6. And then these numbers simply cross over. The 3 comes down here next to oxygen, the 2 comes down here next to aluminium, so the formula of aluminium oxide would be Al2O3. Let's do another one, magnesium chloride. So the formula for magnesium chloride, we first of all work out the charge on the ions. Magnesium would be a 2 plus because it's in group 2 of the periodic table. Chloride would be Cl1 minus because it's in group 7. These numbers cross over again, so we get Mg1 minus, so we'd put a 1 there, but we don't show 1s. We know that there's 1 magnesium if there's nothing next to it. And then Cl, that 2 has come down next to the Cl. So the formula of magnesium chloride would be MgCl2. I've got more practice at these in a whole video devoted to working out ionic formulas, and that's in my playlist C3. I'm now going to show you what ionic compounds are actually like. In other words, we're going to look at their properties. And to understand their properties, we need to take a look at how the ions are arranged. So the positive and negative ions are arranged in a giant ionic lattice. It's called a giant lattice because there's thousands of ions joined together, and the lattice refers to the fact that it's a regular pattern, nice neat rows. And what's holding those ions together are very strong electrostatic forces. The positives and the negatives are attracting each other together. The first property I'm showing you here is melting point. Here I've got some sodium chloride, a typical ionic compound, and it's been heated up quite strongly by this Bunsen burner for a few minutes now, and it's showing no signs of melting. That tells me that an ionic compound like sodium chloride has a high melting point. The reason ionic compounds have such a high melting point is these strong electrostatic forces between the ions. A lot of energy needs to be put in to overcome these forces. I'm now going to test if ionic compounds conduct electricity, and I'm using some sodium chloride as my ionic compound, and I've got two electrodes here connected to a bulb and a power pack. So if we test the solid ionic compound, we can see the bulb doesn't light up, therefore it's not conducting electricity. But let's see what happens if we add it to water and make that into a solution and give it a good stir. Now I must say, don't normally put electricity through water because it's very dangerous, but I'm just using a power pack to keep the voltage and current very low. So let's test if the sodium chloride solution conducts electricity, and we can see by the bulb lighting up that now it's a solution, it does conduct electricity. And if we had managed to melt the sodium chloride, we'd also find that in the molten form it conducts electricity. So when solid, ionic compounds don't conduct electricity, but when they're in some form of liquid, then they do conduct electricity. The reason the ionic compound doesn't conduct electricity when it's a solid is these strong electrostatic forces hold the ions in place, so the ions aren't free to move. Whereas if we've made it into a liquid, either by adding it to water and making it a solution, or we've melted it, now the particles can move around, so the ions are free to move. We've already seen how a metal atom and a non-metal atom react together by ionic bonding, where the metal atom gives away one or more electrons to the non-metal atom, forming ions in the process. We're now going to take a look at how non-metal atoms join together by covalent bonding. The first example I'm going to talk you through is fluorine, how it makes F2 molecules. Well, if we look at two fluorine atoms, it's in group 7, so we can see each of these atoms has got 7 electrons in the outer shell. Now, it clearly can't join together by ionic bonding, because if this fluorine atom gave an electron to this one, okay, this one would now be stable with a full shell, but now this one's even further away from being stable, because it would only have 6 electrons, and ideally it would like 8. So what happens instead is the atoms get close enough together so that their electron shells overlap. And if we put on the 7 electrons of this atom and 7 electrons of this atom, we can see that this atom's got 7 electrons, so it needs 1 more to be stable. So what happens is it shares one of these from the other atom. So we'll put that electron there in what I like to call the sharing zone. If this atom is sharing 1 electron to that one, this one shares 1 back. So we'll slide this one round into the sharing zone. We can still see that each atom has only got its own 7 electrons, so this one has still got 7 crosses. We've not put more crosses on there. Likewise, this one has still only got 7 dots. We've not suddenly invented more dots. But by sharing, we can see that now each atom has got a full outer shell. 2, 4, 6, 8. So that atom is stable. 2, 4, 6, 8. And that atom is stable. And this is what we call a covalent bond. It's a pair of electrons being shared between 2 atoms. And the other way we could show it is with a stick. And that stick is a covalent bond that represents those 2 electrons being shared between these 2 atoms. Let's look at a slightly different example now. So we've got 2 atoms of oxygen that join together to form an oxygen molecule, O2. Now, I've already put the electrons on their outer shell. We're not showing the inner shell because they don't do anything. Oxygen is in group 6 of the periodic table, so each oxygen atom has 6 of its own electrons. So this time, if it's got 6 electrons, it needs 2 more to be stable with a full outer shell. So it's going to share these 2 electrons from this atom And if that atom is sharing 2 electrons with this one, this shares 2 back. So I'll slide these 2 electrons round. And we can see there that we've now got full outer shells on both atoms. 2, 4, 6, 8, that's full, and 2, 4, 6, 8, that one's full. And the way we show this with sticks is we've got our 2 oxygen atoms, we've got a pair of electrons there, and we've got another pair of electrons there. And we call this a double covalent bond. I also wanted to show you this example, methane, because it involves hydrogen atoms. So I've already drawn the electrons on, but I've been careful not to put them in the sharing zone just yet. So each hydrogen atom has just 1 electron, and carbon is in group 4, so it's got 4 electrons in the outer shell. There they are. So what we need to remember about hydrogen is this is that first shell that only needs 2 electrons to be full. So each hydrogen atom only needs 1 more electron, whereas the carbon atom, that's the second shell, and that needs 8 in total to be full. So this hydrogen, to fill that first inner shell, needs 1 more electron to be stable. So we're going to move 1 round from carbon, put it in the sharing zone. If carbon is sharing 1 electron with hydrogen, hydrogen shares 1 back. Similarly, this hydrogen, this first shell, needs 2 electrons altogether to be full, so it needs 1 more electron. So carbon shares 1 of its electrons with this hydrogen, and hydrogen shares 1 back. Same with this one, it needs 1 more electron. Let's move this one round into the sharing zone, and that hydrogen shares it back. And finally, this hydrogen atom does exactly the same. It gets 1 more electron that it's sharing from carbon, and it shares 1 electron back. So if we look at each hydrogen atom, they're now stable with 2 electrons filling that first shell. And carbon, this is the second shell of carbon, remember, so it needs 8 electrons altogether to be full and to make the atom stable, and it's now got 2, 4, 6, 8. To draw the stick diagram for this one, we can put the carbon atom in the middle. We've got a hydrogen either side and above and below. And between each hydrogen and the carbon, there's just 1 pair of electrons, so we only need to draw 1 stick. So that would be the other way of showing covalent bonding in a molecule of methane. When non-metal atoms join together by covalent bonding, they can either make small molecules made from just a few atoms joined together, they're called simple molecules, or they can make giant covalent structures made from thousands of atoms joined together. And we're going to start with those simple molecular substances made from simple molecules, and the example I've got here is sugar. And the first thing I'm going to do is heat it up to see if it's got a high or low melting point. It's not taken much heat energy at all from the Bunsen burner to melt the sugar, and in fact you can see it's now also boiling. So that suggests that simple molecules have a low melting point and also a low boiling point. I'm now going to test the electrical conductivity of this sugar, which is a simple molecule, and I've got a circuit here, and in the circuit I've got a bulb and I've also got 2 electrodes. And if I use my metal spatula to connect the electrodes, the bulb should light, which proves that the circuit is working absolutely fine. So now I'm going to put the electrodes in the solid simple molecular substance, and we can see as a solid it doesn't conduct electricity. But how about when we add it to water and make it into a solution? If we remember, the ionic substance did then start to conduct electricity once we'd made it into a solution. Well, with the simple molecular substance, we can see that even when it's in a solution, it still doesn't conduct electricity. So simple molecules or simple molecular substances don't conduct electricity at all. I'm now going to explain why simple molecular substances have low melting points, low boiling points, and they don't conduct electricity at all. But we need to think about the structure and bonding of those substances. Now, if we take the example of carbon dioxide, it's a simple molecule. We've got non-metal atoms joined together, and we've only got a handful of atoms joined together in each molecule. In this case, 3 atoms, 2 oxygen atoms and 1 carbon atom. Now, holding the molecule together, we've got these strong covalent bonds, which we can call strong intramolecular forces. Intra meaning inside, so strong forces within the molecule. We can also see that there's weak forces of attraction between the molecules, so we call these weak intermolecular forces. Inter meaning between. So because they've only got weak forces between the molecules, to get the substance to melt or boil, you don't need to put much energy in to overcome these forces. So therefore they have low melting points and low boiling points. We can also see why they don't conduct electricity at all, because there's no charged particles that can move around. There's no, for example, delocalized electrons, and there's also no ions that can move. We've seen how a few non-metal atoms can join together by covalent bonding to make simple molecules or small molecules. We're now going to have a look at how thousands of non-metal atoms can join together by covalent bonding, and in this case they make giant structures. The first giant structure I'm going to show you is diamond, and diamond is made from thousands of carbon atoms joined together by covalent bonds. And we can see in diamond each carbon atom makes 4 strong covalent bonds to other carbon atoms. In graphite, we can see the carbon atoms are in layers, and between the layers we've got weak forces between the layers. If we look down upon the layers, we can see the carbon atoms are arranged in 6-sided hexagons, and each carbon atom this time is making 3 strong covalent bonds with just 3 other carbon atoms, whereas in diamond each carbon atom was making 4 covalent bonds. Now, graphite is found down the middle of pencils, and one property of graphite is that it is very soft. So if you press on the pencil too hard, we all know what happens, and it breaks. Here I've got a pencil that's sharpened at both ends so that the graphite is sticking out from the wood, and I've connected it into a circuit with a bulb and a power pack. And if I switch the power pack on, we'll see the bulb lights up, which shows that the electric current is flowing down the wires, through the graphite down the middle of the pencil, back through the bulb and back to the power pack. So this shows that graphite quite clearly conducts electricity. In this demonstration, I'm going to attach a drawing pin to this very long piece of graphite using petroleum jelly. And then I'm going to heat up the other end with a Bunsen burner, and we'll see what happens. So what's just happened is, as we've heated up this end of the graphite rod, the heat energy has managed to travel along the graphite till it's got to the petroleum jelly. That's caused the petroleum jelly to melt, and then the drawing pin has fallen off. This clearly shows that graphite is a good conductor of heat energy. To get the best marks on this topic, you need to be able to relate the structure and bonding of a substance to its properties. So let's look at diamond as an example. First of all, diamond is a giant covalent structure. That would get you 2 marks in an exam. The giant part means there's hundreds and thousands of atoms joined together. We're just seeing a small section of it here. And the covalent is because it's non-metal atoms joining together. In this case, many carbon atoms joining together. And we can tell from the sticks in the diagram that that's a covalent structure. Each of those sticks is a covalent bond. It's made of carbon atoms. Each of those black dots is a carbon atom. And each carbon atom is joined to 4 other carbon atoms by strong covalent bonds. Don't make the common mistake in an exam, which is saying there are 4 covalent bonds in diamond. That's not correct. What you really mean to say is each carbon atom makes 4 covalent bonds. And if you put the word strong in front of covalent, that gets you another mark. So we say each carbon atom is joined to 4 other carbon atoms by strong covalent bonds. If we look at one carbon atom in particular, then it's in group 4, so it's got 4 electrons in the outer shell, and we know that shell needs 8 to be full to make the carbon atom stable. So it shares electrons with 4 other carbon atoms. That means all of those outer shell electrons are involved in bonding, and there's no spare electrons or free electrons that can move around. So in diamond we say there are no delocalized electrons. Let's now try and explain the properties of diamond by talking about its structure. Now, properties are what you can say about a substance. The structure is how the atoms are joined together and how they're arranged. So I've put them in 2 different colours so you can make the distinction between a property and the structure. First of all, diamond is very hard, not strong but hard. It's one of the hardest natural substances on Earth because every carbon atom is held in place by 4 strong covalent bonds. It's got a high melting point and boiling point, once again because each carbon atom is held in place by 4 strong covalent bonds, and they're going to need a lot of energy to break those bonds. It doesn't conduct electricity because there's no delocalized electrons. We can see there's some similarities and differences with graphite. First of all, it's still a giant covalent structure. It's giant because there's lots and lots of atoms joined together. Covalent, we can see those sticks between the atoms, those covalent bonds. Still made of carbon atoms, exactly like in diamond, except they're rearranged differently, as we can see from the diagram. This time, each carbon atom is joined to 3 other carbon atoms. And the carbon atoms are arranged in definite layers. Now, each carbon atom is bonded to 3 other carbon atoms by 3 strong covalent bonds. But the layers themselves have only got weak forces between the layers of carbon atoms. And if we look at one carbon atom on its own, it's got 4 electrons in the outer shell just as it had before. But this time it's only bonding with 3 of those electrons. So that means this electron at the bottom is what we call a delocalized electron. That means it can move through the structure, and that will become important when we look at graphite's properties. If we look at the properties of graphite and explain it by talking about its structure, it's very soft and slippery. We know how easy it is to break a pencil compared to the very, very hard diamond, and it's made of the same atoms just arranged differently. So very soft and slippery, and that's because the layers of atoms can slide past each other because there's those weak forces between the layers. And when you use a pencil, it's dragging a few layers of carbon atoms across your page. Graphite has got a high melting point and boiling point because each carbon atom is held in place by 3 strong covalent bonds. It does conduct electricity this time because it's got those delocalized electrons that can carry the charge through the entire structure. And it also conducts heat because those delocalized electrons can carry thermal energy through the entire structure. So once again, make sure you can remember what 4 properties graphite has and the reason it has each of those 4 properties. Here's a typical exam question asking you about silicon dioxide, and straight away the thing that we notice is it looks a little bit similar to the structure of diamond. So the question is, describe the structure and bonding of silicon dioxide, and I would say pause the video, have a go, use the diagram to prompt you, talk about what type of bonds are in the structure and how many bonds each type of atom is making. Okay, let's see how he got on. So first of all, it's a giant covalent structure. That would get you 2 marks, one for saying giant, one for saying covalent. Each oxygen atom, if we look at the red atoms, is joined to 2 silicon atoms with covalent bonds. And each silicon atom joins to 4 oxygen atoms with covalent bonds, with 4 covalent bonds. Part B asks us to predict whether silicon dioxide would have a high or low melting point, and explain your answer by referring to its structure and bonding. So we're remembering it looks quite similar to diamond. Have a go at this, pause the video, then see how you got on. So it would have a high melting point because all of the atoms are held in place by strong covalent bonds that need a lot of energy to break. Notice how every time we mention covalent bonds we put in the word strong in front to get us an extra mark. So the marks here would be 1 mark for saying high melting point, 1 for saying strong bonds, 1 for saying covalent bonds, and 1 for saying they're going to need a lot of energy to break those bonds. This model represents graphene, which is another giant covalent structure made of carbon atoms joined together by covalent bonding. Now we can see that the carbon atoms are arranged in hexagon shapes, 6-sided hexagons, and each carbon atom is joined to 3 other carbon atoms by covalent bonds. We know that carbon atoms have 4 electrons in their outer shell. If only 3 of those are involved in bonding, it means once again it has those delocalized electrons. So graphene can conduct electricity. Because it's only 1 carbon atom thick, it's very flexible and it's also transparent. But it is very strong because this giant structure is held together with strong covalent bonds holding all the atoms in place. I'm now going to show you some molecules called fullerenes. What makes this a fullerene is it's a hollow cage-like structure made of carbon atoms joined together by covalent bonding. This particular one is made from 60 carbon atoms joined together and it's shaped a bit like a football, and this one is called Buckminster fullerene. And we'll notice that the carbon atoms this time are arranged in hexagons and also pentagons. This time also the carbon atoms once again have 3 covalent bonds, whereas they could make 4. That means that there's going to be delocalized electrons, so this particular fullerene will conduct electricity. Also, because it's so small, it's got a high surface area to volume ratio. So for that reason, in the future, it could be used as a catalyst. Other possible uses in the future for Buckminster fullerene could be superconductors in computers because of those delocalized electrons. Here's another type of fullerene. We can tell it's a fullerene because it's a hollow structure made of carbon atoms. And I've tried to show the carbon atoms here with these small pieces of plasticine. This is called a carbon nanotube. The nano part of the name tells us it's very, very small. To be specific, it's between 1 and 100 nanometers in size. Now, because the carbon atoms are only joined to 3 other carbon atoms with covalent bonds, that means there will be delocalized electrons, so the carbon nanotubes can conduct heat and they can also conduct electricity. Because the carbon atoms are joined together with strong covalent bonds, the carbon nanotubes have a very high tensile strength. That means you can try and stretch it and pull it and it won't snap. In the future, these could be used to treat diseases like cancer. They could be injected into the patient's body, and before that, the carbon nanotubes will have been packed full of the drug. This will go around the patient's body to the site where it's needed, and then those drugs will come out of the nanotube and that will treat that particular part of the patient. So make sure you know all about carbon nanotubes. We've already seen how a metal and a non-metal atom react by ionic bonding. We then looked at covalent bonding, which is between non-metal atoms. We're now going to have a look at metals and metallic bonding. This piece of copper is a typical metal. It's shiny, it's flexible, and when it's in this circuit, if I switch the power pack on, we can see the bulb lights up, so the electricity is passing through the copper and back to the power pack. So it's also a good conductor of electricity. If I try heating up the same piece of copper in a Bunsen burner flame, I could keep it in there a long time and it's not going to melt, because metals have a high melting point. To understand the properties of metals, we need to understand their bonding, and it's called metallic bonding. And metals are made of these positive metal ions because the atoms in metals only loosely hold on to their outer electrons. So those outer electrons can float off, leaving behind positive metal ions. And they're in a regular pattern, very close together. They can't move around. All they can do is vibrate. In between the positive metal ions, we've got these delocalized electrons. Delocalized means the electrons are free to move around. So why do metals have such high melting points? That's because the ions are held together by very strong electrostatic forces. And those electrostatic forces are between the positive ions and the negative electrons. Also, metals are good conductors of heat and good conductors of electricity. That's because they have these delocalized electrons. So in a circuit, the delocalized electrons are able to flow through the whole structure and carry the electric charge with them. If we heated up one end of a metal, the other end would get hot because it's conducting thermal energy, and that's because these delocalized electrons once again can move through the whole structure and carry the thermal energy with them. I'm now going to talk about alloys. An alloy is a mixture of a metal and at least one other element. Now, in the example of steel, it's a mixture of a metal and a non-metal because it's iron and carbon mixed together. But it could equally be a mixture of two different metals. For example, brass is a mixture of copper and zinc. And by mixing the metal with another element, we get different properties. And that's what we're going to look at now. Here I've got a very thin piece of iron. It's an iron wire, and I've got a weight suspended from it. And I'm going to gradually add more and more weights until the iron breaks, and that way we're testing the strength of it. And I'll speed the film up to make it a bit quicker. So the iron broke with a mass of 1,500 grams. This time I'm going to repeat the experiment, but I've got a piece of steel wire. And steel is an alloy made from iron with a small amount of carbon mixed in with it. This time it took 1,900 grams to break the steel, so steel is clearly much stronger than the pure iron on its own. So why was the steel so much stronger than the pure iron? Well, in pure iron we can see the atoms are all the same size because we've only got iron atoms. That means that the atoms can slide over each other, and that makes the iron too soft to use on its own. We wouldn't use pure iron to make something like a bridge that needs to be strong. If we compare that to steel, steel is an alloy made from iron atoms and a few carbon atoms in there as well. And because we've now got different sized atoms, it disrupts the layers, so it's no longer in layers, and that means the atoms can't slide past each other anymore, and that makes the steel much stronger. So now that we've covered ionic bonding, covalent bonding and metallic bonding, don't forget to check out those videos with the black and yellow thumbnails. They're the exam question walkthroughs. Also have a look at my website, revisechemistry with mrb.co.uk.